Hey class, today we're going to continue on with talking about Chapter 8, Section 2, and we're going to spend actually a little bit time on this section, specifically because it just takes a little bit of practice, and we want to make sure we really understand Section 2 before we move on to Section 3 and 4. So we're going to bring in this idea of the octet rule in covalent bonding. Again, remember the octet rule. What is the result of electrons sharing within covalent bonds? Well, in covalent bonds, electron sharing occurs so atoms attain the electron configuration of a noble gas. Again, this is the octet rule, but instead of transferring electrons, they're sharing. So the octet rule actually applies to both ionic bonds and covalent bonds. They just do it two separate ways. Ionic bonds involve a transfer of electrons, whereas covalent bonds, we share those electrons. So the combined atoms usually are going to try to get 8 electrons, or an octet, again by sharing electrons. Things that are going to do the sharing of electrons are all my nonmetals, because covalent bonding is between two nonmetals or metalloids. This involves groups 4A, only some of those elements, not all of them. 5A, 6A, and 7A are going to be the ones that likely are going to form those covalent bonds because those are the groups that are majority nonmetals. However, there is a special one that will not get the same electron configuration as 8 valence electrons, and that is hydrogen. Hydrogen is okay with attaining the electron configuration of helium, and it's because helium is still a noble gas. It's just a noble gas with 2 electrons. So the way that it obtains 2 electrons is we will have a single hydrogen atom right here. It has 1 valence electron. And then we have another hydrogen atom that has 1 valence electron. And instead of one stealing it from the other, essentially what they do is they share it between them. So they each are sharing 2 electrons. And that's how they complete the octet there. Now, covalent bonds can be shown a lot of different ways. One way that we can show them is with a pair of dots. So here in red, we see that this carbon is sharing 2 electrons with this hydrogen. Over here, this bromine is sharing 2 electrons with this bromine in order for all of them to have 8. Even over here, this oxygen is sharing 2 electrons with hydrogen, so oxygen has 8, and then hydrogen has 2, and that's okay. We just talked about on the last slide, it's okay if it has 2. We also can share it using a single line. Whenever you see a single line, that is equal to 2 electrons. So over here, we have a dash or single line. This represents 2 electrons being shared. Anytime electrons are being shared between atoms, we call these bonding or shared electrons. We call them bonding because, again, they're bonding something to carbon. And again, we are sharing those electrons between 2 elements. Now, a pair of valence electrons that is not shared between the atoms, we call these unshared pairs. Oftentimes, you're going to hear me call them lone pairs, or they can also go by non-bonding pairs. The reason lone pair is bolded and underlined is because that's often what I call them. So if we look at this image down here, the shared pair is between nitrogen and hydrogen because I see them between 2 atoms. But this pair down here is considered a lone pair because it's not bonding to another element. There's no 2 elements right there next to each other. Now we can go into, there are actually different types of covalent bonds. There are something that we call single covalent bonds, double covalent bonds, and last but not least, there are something called triple covalent bonds. So what is a single covalent bond? Whenever 2 atoms are held together by sharing 1 pair, so remember 1 pair is 2 electrons total, they are going to be considered a single covalent bond. Hydrogen is a good example of something that will form a single covalent bond. Again, we're going to bring that picture back up. We have hydrogen. Here we have a hydrogen, and they are going to combine and share this 1 pair of electrons. So this tends to form a single covalent bond. Again, you can write it like this with 2 dots, or you can write it with a dash, and this means, again, that they're sharing 2 electrons. Halogens also form a lot of single covalent bonds, and you would note, based on the last lesson, halogens are one of those ones that typically form diatomic molecules as well. So fluorine can actually bond with itself to form diatomic fluorine. Here we have fluorine with 7 valence electrons. This fluorine has 7 valence electrons. Essentially what they do is they take these 2 electrons and share them between themselves in the middle. And that is so the fluorine over here on the left has 1, 2, 3, 4, 5, 6, 7, 8, and the fluorine on the right has 8. However, they're only sharing this one pair, so therefore they're completing the octet rule and actually have the same electron configuration of neon, so they're happy. Again, you can illustrate this with 2 dots, or you can illustrate it with a line, which means 2 electrons. You can also see single covalent bonds happening between oxygen and hydrogen whenever we have a water form. So for example, one of these hydrogens with 1 valence electrons will actually bond here. The other hydrogen with 1 valence electron will actually bond here. And so we end up getting a structure where oxygen has 8 around it. Hydrogen's okay with having 2, so we've completed our octet. So you can write it as such here, or you can replace those shared electrons with dashes, and both of these structures are considered correct. Then we get into the point of double and triple covalent bonds. And they're going to sound exactly what the name implies. If a single covalent bond shares a single pair, a double bond is going to actually share 2 pairs of electrons, and a triple bond will actually share 3 pairs. And the reason they do that is because, again, they still want to attain the noble gas configuration or structure that we're striving for with the octet rule. Double bonds, if we're going to look at an example of this, again, involves 2 shared pair of electrons, which is 4 electrons total. Diatomic oxygen, or O2, is a good example of something that will have a double covalent bond. If we look at oxygen, each oxygen actually donates 6 valence electrons plus 6 valence electrons, which means I can only work with 12 electrons. Can't have any more than 12 and can't have any less than 12. So in order to get a full 8 electrons around it, they have to actually share 4 electrons, or 2 pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here we can see that this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So it's complete octet. You can see the other side also completes the octet. You can write it as 4 dots being shared between them, hence the 4 electrons, or you can draw the 2 lines, hence the double bond or 2 pairs being shared. Another example of something that has a double covalent bond is something like carbon dioxide, or CO2. It actually, in order to complete a full octet, we have to have both those oxygens double bonded to carbon, and we can illustrate them again as 4 dots or 2 lines being illustrated. Last but not least, we have triple covalent bonds. These are going to share 3 pairs of electrons, or we're going to say a total of 6 electrons. An example of something that forms a triple bond is nitrogen. A diatomic nitrogen, which is N2, so 2 nitrogens bonded together, typically are going to have to form a triple bond in order to get 8 valence electrons. The reason for this is a single nitrogen can give 5 valence electrons. So if we have 5 from one nitrogen, we get 5 valence electrons from the other one. So I can only have total of 10 electrons that I'm working with. Again, I can't have any less or any more. So in order to get a complete octet, these have to be shared, these 2 have to be shared, and this one has to be shared. When they share those, we end up getting 1, 2, 3, 4, 5, 6, 7, 8 on the left, and then 8 on the right. So everyone completes their octet. We can illustrate it with 6 dots, indicating the 6 electrons, or we can indicate with 3 lines or 3 pairs of electrons. That's where it gets its name, triple bond. Now, how do we actually draw these? How do we come up with these and figure out what kind of bond am I having and who's bonded to who? So here is a list of rules that we're going to go over and give some examples of how to draw these. Rule number 1 is we actually have to count up how many valence electron each atom has in order to figure out how many available electrons I have to work with. Again, you can't have less or more than the allotted amount. So we're going to go down here and look at example number 1 and add up how many electrons we are allowed to have for each of these. So carbon can actually donate 4 valence electrons. Hydrogen can actually donate 1 valence electrons, but I have 4 of them based on my formula. So here I get 4 plus 4. I have 8 electrons total that I'm allowed to work with. Step 2, draw the skeleton structure, and we need to determine who is the central atom. Typically, this is going to be the atom that's listed first because it's usually the least electronegative atom. You have electronegativity chart located on the very back of your periodic table if you're just curious. However, one thing, if you are given carbon, carbon is almost exclusively in the middle, and hydrogen and halogens are typically not going to be the central atom. So again, you're going to look to see who's listed first, but if you're given carbon, smack carbon in the middle. So if we look at our example, we're given carbon and it is listed first. So we're actually going to put carbon in the middle and we're going to put the other hydrogens around carbon. Okay. Step 3, we're going to place a line, or we call this a bonding pair, between each atom. Remember, a line counts as 2 electrons. Then we must subtract the number of electrons that we actually used. So here, let's make a line between all these electrons around our central atom. Remember, a line is 2, so we use 2, 4, 6, 8 electrons, and that gave me 0. I have no more electrons that I am allowed to place. Oops. Rule number 4, if we have any remaining electrons, we should make sure the outside's happy first. We don't have to worry about that rule because we did not have any electrons remaining, so we're going to go to rule number 5. Check to make sure everyone is happy with the octet rule. So if the central atom does not meet it, that is when we're going to have to move electrons around and form a double or triple bond. Thankfully, when we go down to our example, carbon has 2, 4, 6, 8 electrons around it, so carbon is happy. And then if we actually look at our rule, it says hydrogen is okay with just having 2 electrons around it. So hydrogen is okay with just having 2. If we look at our example, hydrogen has 2, so we're good. Structure A is complete. So let's look at our next example, CS2. Carbon can donate 4. Sulfur has 6 valence electrons, but I have 2 sulfur. So here I just need to add up how many I'm allowed. 4 plus 12 gives me I'm allowed 16 electrons. Again, rule number 2 says who goes in the middle. So right now, carbon is actually listed first, and carbon should always go in the middle if you have it. So we're going to put carbon in the middle, and then we're going to put sulfur on either side. It doesn't matter if it goes left to right or top to bottom. I just like to write them like this so it's looks symmetrical. Here, I'm then going to make a bond between these atoms, and here I use 2 electrons in this bond, 2 electrons in this bond, so I used 4 electrons. Now I'm allowed 12. In this situation, we now have leftover electrons, unlike the example before this. So let's see what happens to my remaining electrons. It says place the remaining electrons around the outside atoms to satisfy the octet rule. So if any electrons are left over, then we can put them on the central. So again, we're going to make the outside happy first and then put any remaining on the middle. So here, sulfur has 2, 3, 4, 5, 6, 7, 8. So I use 6 electrons there. Now I got 6 left. Okay, this one has 2, 3, 4, 5, 6, 7, 8. So I've used 6 electrons here, so I have 0. I have no more electrons I am allowed to place. So let's go back up to my rules. Okay. Check to make sure everyone is satisfied by the octet rule. So if we look down here, sulfur has 1, 2, 3, 4, 5, 6, 7, 8. This sulfur is happy. Sulfur over here, 1, 2, 3, 4, 5, 6, 7, 8. So this sulfur is happy. But if we look at carbon, 1, 2, 3, 4. Carbon only has 4, not 8. So let's see what we got to do. If the central atom does not meet the octet rule, we need to move 1 or 2 lone pairs of electrons and form a double or triple. Note that hydrogen and halogens will not typically form that double or triple, so we need to take from elements other than hydrogen or halogens. So here we have sulfur, which is not a hydrogen or halogen. We can actually take these electrons and move them here, and we can actually get a double bond here. So this can actually be written as carbon with 1, 2, 3, 4 instead of 6 pairs around it. And then here we get sulfur, 1, 2, 3, 4, 5, 6. Now we look at here and sulfur's happy still, sulfur's happy still, carbon is still not happy. So we need to form another bond in order to make carbon happy. I always try to make sure that these are going to be as symmetrical as possible. So what we're going to do is we're actually going to take this pair of electrons and move it down. So now we get carbon, still double bond, 2 electrons. We get a double bond here. So instead of having 6 around it, we're only going to have 4. And then notice here, if we look to see if everybody's happy, carbon now has 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy. It forms 2 double bonds. On our next example, let's add up. Nitrogen gives us 5. Iodine has 7 valence electrons, but I have 3 of them. So 5 plus 21 gets me 26 electrons that I am allowed to work with. Again, typically it's going to be that first element listed, which is nitrogen. We're going to put the iodines around it. And then we're going to make our initial bonds. Here I use 2, 4, 6 electrons since I had 3 bonds being made. Now let's go back to my rule. If we have remaining electrons, we are going to make sure the outside is happy first. So here my outside, this iodine has 2, so I need to get it to 8. So I'm going to add 6 electrons around each of those iodine and make sure that I don't go over how many I have left. Okay, so I placed 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. And that leaves me with 2. So I have 2 more left over. If any electrons are left over, assign them to the central atom. So we're going to put them back on that middle atom. So we're going to put 1, 2 here, and this gets me to 0. Last but not least, make sure everyone satisfies the octet rule. So iodine has 8, iodine has 8, 8, and then even nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 around it, so everything's happy. On our next one, carbon can donate 4. Oxygen is in group 6, so it has 6, which means we are allowed to have 10 electrons. Notice here I only have 2 elements, so nobody can actually be in the middle. We're just going to have carbon bonded to oxygen. So we're going to use 2 of those electrons, and I have 8 left. Here, we're just going to try to make sure everyone's happy. A lot of times people put 8 electrons and split them equally, and so that uses up. But then we have to check, are we happy? We're not. Carbon has 1, 2, 3, 4, 5, 6. Oxygen has 6. So what we're going to have to see happen is we're going to have to move these electrons. These are going to have to move down here where we get a double bond between oxygen and carbon. Now instead of having 2 pairs on carbon, I have 1. So carbon's not happy, but oxygen is. And so since we're still not happy, this is where we're going to have to make a triple bond. So here we're going to have to take these pair of electrons and move them here. So again, we're going to get a triple bond now between oxygen and carbon. So it takes out this drawing. Now instead of having two pairs on this one, I just have one. I just have one pair here. Notice my final structure still has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Still only has 10 electrons, but everyone satisfies the octet rule. Carbon has 8, oxygen has 8. And then our last example, sulfur dioxide. Sulfur can donate 6. Oxygen can donate 6, but there's 2 of them. So 6 plus 12, I get 18 electrons I'm allowed to use. Sulfur is going to go in the middle because it's listed first, unless it's carbon, which I don't have any carbon. And so I need to bond these with 2 oxygens. I used 4 electrons here, which gave me down to 14. The rule says if I have any left, satisfy the outside first. So 1, 2, 3, 4, 5, 6. Got my 7, 8 right there. 1, 2, 3, 4, 5, 6. I got my 7, 8. I have actually placed 2, 4, 6, 8, 10, 12 dots. That gives me 2 electrons left over. Whenever we have electrons left over and the outside are happy, we're going to place them on the center. So that gives me 0. Again, double check that the octet rule has been satisfied. Here, this oxygen's happy, this oxygen's happy, but sulfur's not. Sulfur only has 1, 2, 3, 4, 5, 6 electrons around it. So again, this is where we have to take into account, I ran out of electrons, I must make a double or triple bond. Now, who do I take from? In this case, since they're both oxygen, I can take from either one. It does not matter which one you take from. So let's just take from this one and make a double bond there. So I get sulfur with a double bond. Now instead of 3 pairs, I'm only going to have 2 pairs around. I still have these pairs right here. Nothing happened with this oxygen. And then now we can check to see if everybody's happy. Oxygen has 2, 4, 6, 8. Sulfur has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. Everyone's happy, so this one is a perfectly good structure. Now I'm going to have you guys try these on your own. It is completion. I want you to try your best. We're going to actually go through the answers in the following class period. So absolutely try your best. You must give effort, but it is completion, so we'll go over the right answers in the following class period. I hope you guys have a great day and enjoy.